In the world of civil engineering, few names are as ubiquitous as Ralph R. Proctor. Every time a technician swings a hammer or a geotechnical engineer plots a compaction curve, they are walking in the footsteps of a man who transforms soil from an unpredictable natural element into a reliable construction material. Before the 1930s, earthwork was largely a matter of guesswork and intuition. Engineers knew that wet soil behaved differently than dry soil, but they lacked a standardized, scientific method to ensure that a dam or a highway wouldn't simply settle or collapse under its own weight. The breakthrough occurred in the early 1930s while Proctor was working as a field engineer for the Los Angeles Bureau of Waterworks and Supply. Tasked with the construction of several large earth-filled dams, he realized that the stability of these structures depended entirely on how densely the soil was packed. Through meticulous experimentation, he discovered a fundamental principle of soil mechanics. For a given compactive effort, there is a specific amount of water, the optimum moisture content, at which a soil achieves its maximum dry density. This discovery led to the development of what we now call the standard Proctor Test. The procedure was deceptively simple, but revolutionary. By compacting soil into a mold using a specific number of blows from a standard weight hammer dropped from a set height, Proctor could create a moisture density relationship curve. This bell-shaped graph allowed engineers to pinpoint exactly how much water to add to the soil in the field to achieve the tightest possible grain-to-grain contact, effectively creating a blueprint for structural stability. As construction equipment grew larger and heavier following World War II, the original standard Proctor test began to fall short. The light hammers of the 1930s could no longer simulate the massive energy being exerted by modern rollers and vibratory compactors. In response, the modified Proctor test was developed. By increasing the weight of the hammer and the height of the drop, engineers were able to provide a much higher compactive effort, ensuring that foundations for massive airfields and interstate highways could withstand the unprecedented loads of the modern era. The impact of Proctor's work cannot be overstated. His method provided a universal language for quality control, moving soil science out of the realm of art and into the rigors of modern engineering. Because of the Proctor test, we can quantify exactly how compact a layer of earth is compared to its theoretical maximum. It is the gatekeeper of the job site. If the field density doesn't meet the specified percentage of the Proctor maximum, the work stops. This simple test is the reason our skyscrapers remain level and our dams hold back billions of gallons of water. Today, Ralph Proctor's name is stamped on metal molds and printed in laboratory manuals across the globe. While the technology for measuring density has evolved, moving from sand cones to nuclear gauges and electromagnetic sensors, the underlying theory remains unchanged. Every time an engineer looks at a compaction curve to find that sweet spot of moisture, they are utilizing a legacy of safety and precision that began with one man's observations in the California dirt nearly a century ago.